Yeah, let's go ahead and get started. Thanks everyone for coming to today's Beyond the Scope discussion. Today we have David McComb giving a talk on electron energy loss spectroscopy and doing a lot of work on his kind of stuff, doing monochromated stem eels. He's done a lot of work there. He's the director here at CMAS, so I interact with him quite a bit in that role as well as other things, along with his role as the director at CMAS. He is a research professor in material science engineering. So he kind of has two hats here at CMAS, doing research with this and also directing it, doing that, bringing the whole facility together. So I just want to also mention that there are going to be 2 more webinars coming up this semester. So in 2 weeks, right before Thanksgiving, Yoshi will be giving a talk on single particle analysis for cryo-EM. And then to finish out the semester at the start of December, Carly Goodwin will be giving a talk about micro-CT and doing region of interest scanning. So some more different complex topics and some topics that we've covered before. So I think if you move one slide on, Dave, there's gonna be lots of questions. So we try to aim for around 30 minutes on these talks. So hopefully Dave's around there on that, a little bit longer sometimes, but if you have questions during it, feel free to post those in the Q&A, works very well, or the chat if you have any kinds of problems. And at the end, if we start to have more lively discussion as well, and you're interested in talking directly, and it gets to be complex, we can raise our hands and unmute you and have some of those discussions as well. But lots of questions are great. We want this to be a nice discussion. Okay, Dave, pass it on to you.
Okay, thanks, Dan. Thanks everyone for joining us virtually for this Beyond the Scope discussion. I'm going to talk today, as Dan said, about monochromated stem eels. I'll give some illustrations on functional materials. I'll really hopefully spend a bit of time talking about where some of the exciting developments in the field are going, and we've added some new capabilities. Even actually during the lockdown period at CMAS, and I think there are some very exciting new experiments that we'll be able to do or that we can do. So we'll talk a little bit about where the field is going. So in the tradition of, I should say that CMAS continues to supply resources that go beyond just coming to use the facilities. That obviously you can attend one of these webinars. You can also schedule one-on-one consultations with our instrument scientists who cover all of these different topics. And we have also remote access for data analysis if you've acquired data and you want to actually process that from home. So any questions on that, just email us at cmas@osu.edu and someone will get back to you on any of these topics. Just a quick overview of the instrumentation. We're very fortunate at CMAS. We have over 14 instruments within the facility, ranging from our TEMs for physical and life sciences, our SEMs, FIBS, and techniques such as our X-ray micromography and other X-ray facilities. And most of what I'm talking today will be related to our EELS capabilities, which are on the 3 instruments here that I've indicated in the red font. So in the tradition of everyone else giving the webinars, I was asked to say a little bit about myself. So I grew up in Ayrshire, which for those unfamiliar with that, that's down in the southwest corner of Scotland, literally just a few miles from the Irish Sea, so very close to my home. This is the view you would have looking out over into Argyll and look at the Isle of Arran here. Really a beautiful part of the world. And of course, the sun is always shining the way it is in that photograph. I did my bachelor's in chemistry at the University of Glasgow. And then I went to Cambridge. I was at Corpus Christi College, did my PhD at the Cavendish Laboratory, PhD in chemistry and physics. And I stayed on there. I first of all was a research fellow for a fellowship awarded by the Royal Commission for the exhibition of 1851, which is always a very interesting story, because those of you who are not aware of that, the 1851 exhibition was a World Expo that under Queen Victoria's reign, and she asked Prince Albert to coordinate that, and it was a highly successful exhibition and made a considerable amount of money. That's where they built the Crystal Palace. And after the proceeds, after it was finished, then Prince Albert created the Royal Commission for the exhibition of 1851 to disperse the proceeds. And it resulted in, for example, the creation of the Natural History Museum, the Royal College of Music, the Victoria and Albert Museum, and indeed Imperial College. So it really was an amazing success. I left Cambridge, went to Canada for a while, National Research Council at McMaster University. And then I was offered my first faculty position back where I started in Glasgow. So I returned to Glasgow. I was there for about 7 years, and then I moved to Imperial College London, Department of Material Science, which indeed is that building, the Royal School of Mines and the Royal College of Music were indeed founded because of the funds from that Royal Commission, or from that World Expo in 1851. And then in 2011, I was coached to move across to a pond to come across to Ohio State. And obviously with the attraction that, of course, Ohio State has a long history in connection with Scotland. And I raised this question about showing your tartan and show your Scottish scarlet and grey. And indeed, for those of you that don't know, that indeed is the Ohio State University tartan. Plaid, as I was informed recently, is the correct expression in the US, but tartan and the rest of it are in Scotland. So obviously we're talking here from CMAS, and our mission here is to bring together our multidisciplinary expertise to drive the synergy and amplify our characterization capabilities and really challenge what's possible in analytical electron microscopy. And you know, these two scans I often use because they illustrate the diversity of what we're doing. The left-hand side, you see a 3D reconstruction that was acquired by Binbin Deng, one of our staff scientists here. That's from the spinal cord from a mouse, and where we were looking for particular types of motor neuron. And on the right-hand side, you see also a 3D reconstruction. And this is from one of my colleagues, Hamish Fraser, looking at a compositionally complex alloy. But this is not just a reconstruction of the microstructure. Indeed, it's actually a reconstruction of the composition. So we can see in different colors all of the different phases that are present within this, this alloy. And these really illustrate the breadth with which we, the materials that we actually study at CMAS. So we opened in 2013. Simply a while ago now that we were wielding these giant scissors. And having all of these instruments, you know, almost $37 million worth of instruments in a custom designed facility puts a responsibility on us to make those as accessible as possible. And to that extent, we created what we call our electron microscopy collaboratory, where we can basically control all of those microscopes from that digital lecture theater, and as well as teaching and training, we can actually use it to collaborate remotely. And here we see, you know, in pre-pandemic times, I was using that digital theater for exactly this purpose, working with high school students, working with graduate students, working with doing workforce development activities within that digital theater. And indeed, we can connect into that digital theater and connect to all of our microscopes from hundreds of miles away. And we build these remote stations that allow us to, you know, to basically make our instruments as accessible as possible to people from universities hundreds of miles away. So let me come to the topic for today. We're going to talk about eels and monochromation, and then I'm going to show you a couple of examples in different types of photovoltaic materials, and we'll move on to talk a little bit where I think the field is going, and I'll illustrate that with an example of another type of functional material. So the geometry that we're really discussing here is we're normally working in a scanning transmission electron microscope. So we're focusing our electrons into a small probe. I focus that onto the specimen. So in our Themis type microscopes or Themis microscope, this would be a sub-angstrom focused probe. Thin specimen, so we scan the specimen and we look across the specimen, we look at the transmitted signal. And we're going to focus today really on the spectroscopic signal, where the fast electron interacts with the specimen and undergoes an inelastic event. And that inelastic event might be the excitation of a single electron from an occupied state into an unoccupied state, and so we lose a certain amount of energy. Or it may be collective excitation, so we actually can excite the valence electrons of in the sample into the conduction band, but we do it in a collective way, and that means that we excite plasmons, collective excitations. And of course, what we actually see in our spectrum is the largest peak is going to be what we call our zero loss peak or our elastic peak, because this is a thin specimen, and typically these are high energy electrons, and therefore the most likely thing to happen is absolutely nothing. And so the fast electrons pass through the specimen, they don't lose any energy, and we get a peak in our spectrum at zero energy loss. And then as we go up in energy loss, then we see in the region up to maybe about 40 or 50 electron volts energy loss, we see excitations between the valence and the conduction band, including collective excitations such as plasmons. And as we go further out in energy, we're on a decreasing background, we'll then see superimposed ionization edges that are associated with inner shell excitations, where we excite electrons from a deeper lying core level in the solid into the conduction band. And we can use these to not only identify the type of atom present, but we can actually learn about how the atom is coordinated to the other atoms around it in the solid. Now, when we look at EOs, then our EOs spectra are really a convolution of the real spectrum, if you like, the real information that we're looking at, with some sort of resolution function. And we could just call that, using the, following on from the work of Ferdinand Hofer, we can just describe this as, just for the sake of now, an instrument resolution function. We're not too concerned about all of the details into that. And so what we see is something that's a convolution of our instrument resolution function and the structure, and then we see a broadened a spectrum. And one of the things that we do is that we make this instrument resolution function narrower and less spread out in energy, then that will basically result in maintaining some more information into the observed structure. And we can do that, for example, by changing the electron source, whether we go from a thermal lanthanum hexaboride source through to a cold field emission source. And then the development that we really saw in, I guess, 15 years ago or so, was the introduction of electron monochromators. And one of the first commercial electron monochromators was the FEI monochromator. We got a little Lego man or Lego person to show us the scale here that the monochromator sits in the gun. It's about 50 millimeters high. And it's effectively a beam filter type monochromator. And with a Schottky type source, it would take our beam from an energy spread of about 0.5 to 0.6 electron volts to an energy spread of under 0.2 electron volts. Now, in fact, that has been significantly improved on in recent years. So with most monochromated systems, certainly an energy resolution of 200 millielectron volts is possible. On a new Themis operating at lower voltages at CMAS, we can get 30 millielectron volts or better. And then in the neon instruments, we've seen significant improvements over the last couple of years. And most recently, we've seen data reported that is less than 5 millielectron volts. And this zero loss peak just illustrates the effects of changing that full width half maximum from of the order of 175 millielectron volts here at the wider spectrum down to 35 and better. And you can see that the big effect of that is that you remove these tails. Okay, so you get much narrower peak, but you lose all these tails, which means that this part of the spectrum now becomes much more accessible. And that's where we're going to start, because we're going to talk about how we can use monochromated EELs, first of all, to study organic materials. And in these cases, this is the work of Jessica Alexander, who's a PhD student at Greenwich a couple of years ago, and looking at organic photovoltaic systems. And here we were particularly interested in looking at that low loss part of the spectrum, because when we look in this low loss part of the spectrum, we can show that we can analyze this EEL spectrum to obtain something that we call the complex dielectric function. And that complex dielectric function contains all of the information about the optical properties of the solid. And in particular, the imaginary part is really our absorption terms. It tells us about transitions, single electron transitions between the valence and the conduction band. We were able to isolate, using the dielectric function, the single electron transitions from those collective excitations. And the energy of those transitions are going to be related to the bonding, which may change as we look at different, for example, interfaces in organic systems. So that's what we were setting out to do. So we want to look at these organic systems. We want to look at the bonding, and in particular, can we address questions about bonding at interfaces between organic systems? And this is a great topic to look at. It's not just relevant for photovoltaics, it's relevant for polymer composites, relevant for biomaterials, and indeed biological systems. And we can use that dielectric function to get information about a wide range of things, including all kinds of optoelectronic properties. So we're going to look, first of all, really at this organic photovoltaic materials. We want eventually to go to what we call a blended system, where we would have an intimate mixture of our acceptor and our donor phase here. But in order to start this out, we really want to look at what's been done previously, and then look at a simpler system to try and test what's possible. And indeed, there have been some valence loss spectra published by a number of groups previously when we started this work, but really there was a lot of inconsistency in the results. So we really wanted to start afresh. We need a high quality sample. So we actually started, this is actually work that was done at Imperial College before I left. Student James Gilchrist, who was supervised by myself, and Professor Sandrine Hoyts. And this is a cross section of an organic system, but it's an organic layer. It's a bilayer system. So it's a layer of C60 and copper phthalocyanine. And I'm just really showing you this high resolution TEM image just to show that you can make very, very high quality cross sections of these organic materials without actually causing damage. And you see all of the lattice fringes within the material. So we're really very high quality materials. Because we have a bilayer system, we can look at the two phases on their own. So we look at there's a spectrum from C60, and this is the spectrum from copper phthalocyanine, which is our donor and acceptor phase in that simple bilayer. We can get to our complex dielectric function through processing, and this takes us to the imaginary part on the right-hand side. So this is the imaginary part of the dielectric function for those two phases. And then we can actually, you could even take this and we can calculate, for example, things like the optical absorption coefficient. This is where we do this for copper phthalocyanine, and that means that now we can compare the peaks in this low energy part of the spectrum to the predicted excitations between highest occupied molecular orbitals and lowest unoccupied molecular orbitals. And these predictions from the MO theory fit extremely well with what we see experimentally in the case of copper phthalocyanine, and similarly in the case of C60. And so, you know, we're able to get to these low energy regions and to be able to do this kind of work because we were able to monochromate and get that nice zero loss peak. Now, we want to go to a blended system. Here is a device that was drawn by Marian Sosloff at Lockhaven, and this is our blended system. So here's our multi-layer. Now we want to see what's going on within the blended system and see if we can actually get to study what's going on at interfaces. And this raises the challenge for us that now we're going to have to we're dealing with beam sensitive materials, and so we're going to have to work out how we handle beam damage. And you know, looking at the work of Ray Edgerton, we learn that one way that we can think about this is we can say that radiation damage effectively can be thought of as a way that it limits the achievable spatial resolution, because we can only put a certain number of electrons into an area or a volume without causing damage. And then we can spread that over a larger volume and not cause damage. So then we can think about this in terms of a dose-limited spatial resolution. And that dose-limited spatial resolution delta here depends on a number of factors. It depends on the critical dose to damage of the material, that's just a property of the material. It depends, for example, on the signal to noise that we actually want to achieve in our data, detector quantum efficiency of our device, and a number of other factors. So this is going to limit what we can actually achieve. And here we look at, from the literature published here in JPhys Chem C, is some dose-limited or critical dose to damage in a number of organic systems, and the calculated dose-limited resolution. So you can see, for example, in copper phthalocyanine, you should be able to get down to easily deep sub-nanometer, whereas in something like an aliphatic chain, like a paraffin or something, then you're going to be much more limited. So in Jessica's work, we were really looking, first of all, we looked to see what we could see in terms of the overall blend here. So this is from the OPV device in black, and we compare that with our spectra from our pure phases. In this case, it's a substituted C60 and a substituted thiophene system. So these are just averaged over relatively large areas. And then we can pick this peak that we've indicated in blue here, in black here, or by the blue arrow, I should say. And then we can look at how that varies spatially through our layer. And so we could pick these different energy windows for our different peaks, start to map them across this device, and look to see how we can actually, whether we can identify specific features so that we can start to identify functional groups within this blended structure. And this was sort of where we got to within Jessica's work, and now we're trying to build on that as we move forward. And Brittany Ford, who's a PhD student in my group at the moment, is now looking at how we can extend this and move this into a number of other systems and build on this with the new capabilities that we now have. Now, let me talk about a different aspect of using high energy resolution, and that's in inorganic photovoltaics. And this is principally the work of Julia Dietz, who was co-supervised by myself and Tyler Grassman here at OSU. And this is looking at copper indium gallium diselenide. And here our goal was to try and now see what we could do in mapping over a pretty large device. Now, this is a 2-micron scale bar. And in this SIGS device, there are actually compositional gradients built into it in order to optimize the performance. And here, what we really wanted to do was map the band gap. And this is an old problem. I mean, this goes back here quite a while as people trying to map band gaps in different types of semiconductor systems. But the challenge is that the exact shape of this zero loss peak, especially in that tail region, can be very sensitive to, for example, changes in thickness or changes in orientation, channeling conditions. And so it's hard to do this over a large area in an automated fashion without creating artifacts in the data. So if you try to fit your zero loss precisely and you're trying to deal with a large data set, then you'll often end up with errors that result in unphysical values. So one thing that we decided to do with Julia was, well, let's be conservative. Let's deliberately underestimate the amount of zero loss peak that we're going to remove, which means that we know that we won't get anything unphysical, but we do know that when we subtract that zero loss peak, we will get a signal in here that is actually still due to the zero loss peak. It's not due to the signal that we're looking at. So that was our assumption. And then we started to fit Gaussians to these. And we said, well, let's assume that the first Gaussian is associated with the zero loss peak. So let's look at the properties of the second Gaussian. And in particular, what we want to do is go across this large area of this full device. This is the compositional profile. So this is, almost just over 2 microns. That should be a 2 there. In terms of the in terms of the scale of the device, and this is the composition. And now what we want to do is go across here and map the position of the band gap. And this is what we've done here. We measured this from the B parameter of the Gaussian, which we fitted with within some confidence levels, and then we're plotting the position of that peak over that 2 micron device. And if we overplot that with what we would think the theoretical band gap is based on the composition, we can see that it actually maps extremely well. And so we found a robust way to actually measure that effective band gap over a large area in an automated fashion. And we now look at, as we get even better with our zero loss peak, we are now looking at how we can actually improve that further and whether we can actually get an absolute value of that gap. And that's some of the work that Ari Bloomer is also working with myself and Tyler will be looking towards. So maybe in the interest of time, so I'm going to just touch on this very briefly because this goes to a next step forward, which was to then look at this in specific defects within SIGs, or within this type of device. And Julie came up with a very nice correlative workflow where we were using a scanning technique called scanning deep level transient spectroscopy that allowed us to identify regions where we knew there were defects below the surface in this device, and then to lift a Fib sample from a very specific place, correlated, directed by our scanning measurements, and then to go looking for those defects within this lamella that we've lifted out with the Fib in order to see if we could identify that. And so again, in the interest of time, I'll skip over some of the details here, but this is the scanning DLTS that shows us a particular defect that is a 0.56 EV trap that's well known in this type of device. This is a map of the intensity of where that device, where the intensity in the DLTS actually is. And this is the scale of the Fib foil that we're then going to lift out. So we'll lift out that Fib foil, put it in the TEM. We can see in the contrast that we can identify some regions where we have defects and regions without defects. We can see when we look in the defective region, then indeed there seems to be some additional intensity in red here associated with the defect that's absent in the normal region. So again, using a similar approach, now because it's a defect region, we can add our spectrum together from that region, get better statistics in our energy loss spectrum. Now we can fit our zero loss peak much more carefully and precisely because we're only really at this point now dealing with a single spectrum, not an entire array of spectra. Again, we can fit to our Gaussian here, and then we can show that that peak is indeed associated with a transition at 0.56 EV, which corresponds to that trap intensity that we saw in the scanning DLTS. And then we can map the intensity of that peak and show that it really is correlated with the defect. So this is really the first time that we've been able to really identify, a defect within a full-scale device, identify, localize it, and even then go on. So it's here. Go on to identify the chemistry, which again, I'll skip over. We were able to report in this paper in 2019 the exact chemistry of this device and the chemistry of this defect and correlate that with the known electronic properties. So in the last 5 or 10 minutes, I want to just now touch a little bit on some of these some of the new capabilities that are coming into EELS, and we're now seeing the potential of them. And let's go back to monochromation again, and it's the slide that I borrowed from Andrei Kravanek at NEON, and showing the evolution in, for example, the NEON systems of where we've got to in terms of energy resolutions. Again, we're looking at our zero loss peak, and we can see that, most recently we're down to, as I mentioned at the beginning, sub 5 millielectron volts in terms of full width half maximum. So really, we've seen big improvements in this over the last couple of years, and we continue to see improvements as we see these instruments just get better and better. So what does that enable? Okay, why is that exciting? I've indicated that we can get to really low energy parts of the spectrum, and now we're really pushing this such that we're now plotting our energy loss in millielectron volts. And here's a very nice example from the group at Oak Ridge, led by Juan Carlos Adrobo, showing how you can do something that's actually incredibly difficult in the electron microscope, which is to measure sample temperature. And they were actually found a mechanism to do this by doing electron energy gain spectroscopy. Because what we see here in the case of looking at hexagonal boron nitride is that because we're able to get this energy resolution, we see this peak at about 150, 160 millielectron volts, and that's associated with exciting a phonon in the material. So this is a vibrational loss in boron nitride. But phonons are at finite temperature are there within our material. So if we can excite a phonon with the electron, then we should also be able to transfer the energy of a phonon to the electron. In other words, the fast electron here should not only be able to lose energy, it should also be able to gain energy. And indeed, you can see, because of the energy resolution that they were able to achieve here, is the peak associated with the energy gain. But the ratio of the intensity of these is then given by this expression, which is basically our Maxwell-Boltzmann expression for excited state occupation in this system. And therefore, you can use this to actually then determine the temperature of the specimen. And as I mentioned at the beginning, that's a really difficult thing to do in a microscope, because we have such a small specimen. It's sitting in vacuum. If we're trying to heat it, we don't exactly know the contacts. And knowing the exact temperature is quite a tricky thing to be able to do. And this opens up a really new capability. In the early days of looking at phonons in using eels, people assumed that, many of us assumed that this would be limited to relatively low spatial resolution, because it's well established that as we go down in energy loss, then the localization diameter increases because of the long range interaction of these low energy excitations. So this goes down to 1 electron volt. So you can imagine that if we were to take this down on our log scale down to 100 millielectron volts, then we should have a delocalization length scale that's maybe of the order of 30, 40, even greater nanometers. So we really thought this would be the case, but it's still very powerful. And here's some work that was originally published in 2016. I'll show you an update on this, of looking at a guanine crystal. So this is our organic system here. And we see this guanine platelet crystal, and the data here was acquired in what's called aloof mode, because what we can do is we can put the beam outside the specimen, maybe 20 nanometers or something like that, far away from the crystal. But because of the long range interaction, we can still excite the vibrational losses. And we can do that while minimizing the electron beam damage to the crystal. And this is what Rez and his co-workers did. And they were able to then collect, back in 2016, this red spectrum showing our eel spectrum. And now you're also just looking at the vibrational losses. So here in blue is the IR spectrum from guanine. And you can see from the 2016 data that, in fact, we could see, just minimize this because it's in my way. We could see a good correlation between the eels and the IR spectrum. But in black is shown the more recent data that Andrei Kravanek was able to provide, acquired on a neon with a new iris spectrometer. And I believe this data was done with probably 8 millielectron volts, or maybe slightly better. And you can now see we really are starting to resolve all of this vibrational structure under our eel spectrum. So this is allowing us to do vibrational IR, like the equivalent of IR spectroscopy, looking at vibrational losses in organic systems in the electron microscope. This really is incredibly powerful as we start to think about how we might apply this. And a really nice example of how you can do this is done by two groups. One with Robert Klee's group, and where they were looking at actually liquid water. But what they did was they collected the very low energy spectrum from water and also from deuterated water. And you could see that in the case of when the D2O was present, you could see this additional stretch, which is the oxygen deuterium stretch, and this is the OH stretch. And they showed that very nicely, published that back in 2018. And then Jordan Hachtel and the team at Oak Ridge then extended that further by looking here, for example, at L-alanine, very low energy spectrum, looking at that vibrational spectrum. What they did a very obvious thing for a chemist to do, which is, well, let's take this carboxylic acid group and substitute in do some isotopic substitution, in this case with the carbon-13. And here you see the spectrum that you're able to acquire with the eels from the carbon-12 and the carbon-13. So we're able to see that shift of the C double bond O stretch because of the isotopic change. And these two examples from Klee and Hachtel are really the first time that we've ever been able to detect isotopes using any technique in the electron microscope. And so this really opens up many, many opportunities, especially in biological systems. So I think this is a really exciting development. And then just to finish this off is that I said that we could really only do this with low spatial resolution, but the recent work, first of all, theoretical work by Christian Dwyer at Arizona State, and then more recently, the experimental work from Frederick Haig and co-workers at Superstem in the UK have shown that in fact by using impact rather than dipole scattering, looking in this low energy part of the spectrum, you can actually get phonon spectroscopy with relatively high spatial resolution. And that's shown here where they're able to take EEL spectra that are acquired away from the zero order beam, so out here at a different position in K-space, and then that enables us to actually get spatially resolved phonon mapping. And you can see some of the structure in the hexagonal boron nitride here. Now this is still going to be a challenge because these signals are very weak and require long acquisition times and very stable microscopes, as well as the stable energy resolution. But again, you know, a very powerful method. And, you know, again, we're trying to explore how we can use this, for example, at CMAS to actually get to get information around defects in those types of semiconductors that I mentioned earlier. And again, that's a project that Ari Bloomer is taking the lead on. We've also got spectrometer developments, which I'll mention very quickly, is introduction of direct electron detectors, which has really been, you know, the factor that's really has led to the explosion in cryo-EM in life sciences. But we can take that same advantages of direct electron detection that improves our detector quantum efficiency, and then apply it into EELs. And so we can see that if we improve the DQE, that will then lead to an improvement in our dose-limited spatial resolution. And that's what we were able to do just before lockdown, is that we were able to introduce a direct electron detector onto our EEL spectrometer on the Titan microscope at CMAS. And we're now just starting to, now that we're all back and able to access this, starting to explore the potential of what this means. And you know, this leads to just using the DQE, leads to a much reduced point spread function. These two spectra are our zero loss peaks. I get this from Paolo Longo, but as a zero loss peak acquired under identical microscope conditions, the only difference is in green, we have a spectrum required on a direct electron detector, and on red, we have on our conventional CCD detector. And you can see that the reduction in the point spread leads to improved energy resolution without doing anything else in terms of the electron optics. And that then opens up these same kind of comparisons, looking at titanium and strontium edges. And there's a lot of potential, particularly as we look towards higher energy edges, for exploiting this performance. So where would we like to go in the future? In the last few slides, I just want to talk about that. Is we obviously have talked about, we want to get to lower dose spectroscopy. We want to improve that dose limited resolution, and we're taking steps to do that in terms of energy resolution, detector performance. But you know, the things that might then improve that further would be, for example, trying to maximize the impact or the signal that we actually get from our electrons. And one mechanism to do that we're exploring is actually using novel scanning algorithms. And in particular, on the right-hand side here, we see the work of Lewis Jones at Trinity College Dublin is showing the effect of, for example, here is doing a slow scan EELs map And you can see that in this system, you can see the damage that's actually occurring in front of the electron beam, really. Again, it's this delocalization of damage and whatever that's happening. And you see this damage that occurs when we do this slow scan. But using a fast scan and then what Lewis calls smart align approach, we can actually now start to acquire more quickly. And we take fast scans and then add the data together without the noise amplification that we would normally see with that. And now we can get to much better approaches. And so we've installed this smart align system currently on the Triton Themis, and Binbin Wang and Naria Bagwez are looking at this and to see how we can actually exploit this. And then the one tool that we have left at our disposal to increase the tolerance to dose is actually go to low temperature. And of course, we have lots of capabilities now at CMAS to do cryo-EM, but we've seen, for example, from the work of Michael Zachman at Lehigh, and Michael's now continuing this type of work at Oak Ridge, is how we can use cryostem to actually improve, in this case, looking at solid liquids or hard soft interfaces. And there are other areas that have been explored to try and do this. So varying temperature is really the last frontier that we have to study these beam sensitive materials. And back in November, along with Jeff Lingell and Barry Carter, we co-edited guest editors an MRS bulletin where we looked at the potential for cryo-EM in material science. And I would direct you to that December issue in 2019 for some very nice articles from people like Michael as to where the potential is for these types of technique. And just to show you one example of where we want to be able to look at functional materials, I want to just touch on our work on skyrmions. These are topological spin textures found in chiral magnets. This we can think of as a phase diagram, in this case for iron germanium. It's a B20 structure, and what you can see here is a function of temperature and magnetic field. As we vary the temperature in the magnetic field, we create different phases. This is our ferromagnetic phase, this is our helical phase, and in this range we get what we call our skyrmion phase. And here's some work from Brian Esso's PhD, where we are actually just cycling the magnetic field. This is work that was done at 265 Kelvin. And now we can actually see as we go through temperature, at this low temperature, as we vary the field, we can go through the different phases and we see how these different phases actually form as a function of temperature, a function of field, and we can look at how they interact and the role of interfaces. And Naria Bagwez is building on that, looking at geometric, the confined structures, and working also with our student Binbin Wang at how we can then control these different types of structures. But key to this is actually being able to control the temperature. And to do that, we really need better instruments. You can see here the magnetic structure, very beautiful images of the magnetic structure that Maria presented at the M&M conference in 2019. But we really want to be able to vary the temperature so that we can actually get to the right temperature range for this particular system. And that's true for different types of functional materials. So it's not a case of that we just want to go to liquid nitrogen temperature and hold the temperature there. We've got to be able to do variable temperature, but we've got to do it in a way that allows us still to be able to exploit all of the stability and performance down to the atomic scale in terms of our imaging within our materials and devices. So in conclusion, I want to say that monochromated STEM yields is really providing new insights in our functional materials, both in organic and inorganic systems. I actually didn't talk about our molecular magnet work that we're pursuing, but another time. Getting down to milli-electron volt resolution is really showing enormous promise and new capability for vibrational spectroscopy. And in particular, I really think that the role of isotopic substitution could be really very powerful. New detectors, smart scanning algorithms are really having an impact and will have a real opportunity for us to study our beam sensitive materials. And really to take this to the next stage, and especially for in situ studies, quantum materials, and other functional materials, we really need a stable variable temperature 5-axis stage within our micro in order to be able to move this forward. And I think when we look at instrumentation development, this is where we'll really start to see equipment development is the next stage of equipment development in order to facilitate these kinds of experiments. Quick acknowledgement of all the different funding sources, especially DARPA, AFRL, AFOSR, and NSF, and our Center for Emergent Materials. As Dan mentioned at the beginning, we have a couple of upcoming events, presentations from Yoshi Narui on single particle data analysis using Cryospark, and Carly Goodwin doing region of interest scanning using our HeliScan micro-CT. And as always, you can go to cmas.osu.edu in order to get more information on these. And again, if you have any questions about any capabilities, or you have ideas for experiments, or you want to know how you can be trained, or you want to learn about data analysis, then just reach out to us through any of these methods. And I will stop there and hand back to you, Dan.